So last time we overviewed vector operations, and just to remind ourselves of one particular example, I have this formula that is giving me angle or cosine of the angle between two vectors. Okay? So the formula I can easily visualize in 2D and 3D what the angle between two vectors would be. But I'm typically in 3 dimensions. I have two vectors. Okay? I'm going to look at the angle inside the plane that contains both of those vectors. And we're going to take the scalar or dot product of the two vectors, and we're going to divide them by norm of both of those vectors, and in this case we're taking Euclidean norm. So we say that vectors are orthogonal or perpendicular if the angle between them is 90 degrees, or right angle. So basically then cosine theta has to be, in that case, 0. Okay? So basically my test whether two vectors are orthogonal is whether their scalar product is 0. Another term that we're going to use a lot is orthonormal or normal vectors. So I normalize vector if I divide it by its length. Typically we're going to talk about that in 2-norm using 2-norm. And these normalized vectors of length 1, I typically use them to specify direction of something. Okay? So that is so-called unit vector. Vector is the vector of unit 1, of length 1. Yes. Yes. Good job. Oh, we have one person who remembered that. Yes, I did. But please check on me pretty much every time if you don't see me that whether I started recording. So we will call vectors of length 1, we will call unit vectors. Okay. So question for you. Are these two vectors 1, minus 1, and 1, 1, are they orthogonal? Yes. The only thing I have to be careful about is that if I'm strictly applying that formula before that takes transpose of 1, it has to be a row vector times a column vector, right? So I gotta transpose one of them to make it work. Okay? So just make it work. Or I can just use the formula where I take u1v1 plus u2v2, which is 1 times 1 plus minus 1 times 1, and that's a 0. So they are orthogonal. How do I convert them to a unit vector? Can you do that quickly? And while you're doing that, I'm going to switch to my writing pad here. So what's going to be the normalized or a unit vector in the same direction as u? Any guesses? Okay. Bless you. Okay. So basically, if I had u, which is 1 minus 1, what is Euclidean norm, L2 norm, length? Square root of 2. So basically, the normalized vector will be and that's it. Okay, so this is just a vector of length 1 in the same direction. All right. And then we started talking about the matrices. Matrix, I can either look at the collection of row vectors or column vectors. Both ways work. And we started talking about some characteristics. How do I describe a matrix? So let's say that I have 1, minus 2, 3, 3, 1, 7. Okay. What is the dimension of this matrix? You're going to give me a color of the shirt? Black shirt. All right, there's a black shirt that I see right here. So what is the dimension of this matrix? How many rows do I have? How many columns?
2 by 3.
So it's a 2 by 3. So we take number of rows times the number of columns. And then next black shirt. So if I have now actually a vector that is 1 minus 1, like that u, could I multiply these two, this matrix and this vector? Why not? So I don't have enough members, right? So what I need to do in multiplication, I would have to take this row and do essentially a dot product with this column, right? And I don't have enough elements. For that, I have to have the matching number of elements. And we also call that so-called inner dimension. So this is 2 by 1. And these two dimensions do not match. So if they're not the same, we cannot multiply. So I cannot multiply. All right. So essentially, let's actually now find something that we can. And this is actually something, this rule is something that I can do for multiplying matrices as well. So last time we went over multiplying matrix and a vector, right? So now we will actually try to multiply two matrices in the same way. So let's say that my B, or matrix B, is given as 1, 1, minus 0.5, minus 1, and minus 0.5, minus 3. Who else has a black shirt? I see it over there. So can you tell me what is the dimension of matrix B?
3 by 2.
3 by 2. So can I do the multiplication? With A. Yes, because my 3 and 3 are matching. So I can actually multiply. So let's actually do this multiplication AB. I'm going to rewrite them once again. Actually, wrong choice of color, just a moment. I love the fact that I can erase. So what we're going to do is we're going to again match rows and columns. So when I had matrix vector multiplication, okay, I have multiplies basically a dot product of the first row of matrix and this column vector, and that gives me a number, and that was my number in the first row and first column here. And then I have this second row times this same vector will give me the second number, okay, and I can organize them in a column vector. And then I'm going to repeat the same procedure on the second column vector I have. So I'm going to look at this matrix B as a collection of two vectors, two column vectors, and I'm going to repeat matrix vector multiplication twice on both columns. Okay? Does that work? Let's do it. And then it will probably make more sense. So essentially, I have, first I'm going to do this first row and first column. And I'm going to place that result in this matrix. So 1 times 1 plus minus 2 times minus 0.1 is also 1. So that's 1 plus 1 minus 1.5. Am I doing that? I'm going to make my life easy here. And I'm going to place the number 2 here. How's that? So it's going to be just minus 1. So what did we have? 1 times 1 minus 2 times minus 0.5 and plus 2 times minus 0.5. So this is going to be 2 minus 1 is 1, correct? Then I'm going to repeat the procedure with these two. So I actually put this in a blue color. Then I'm going to repeat the procedure with this. So that's going to be 3 times 1 minus 0.5, that's 2.5, and then minus 3.5. Okay, that's 2.5 minus 3.5 is minus 1. Okay. So I'm now done with the first column vector. I'm just going to move over and do the second one. Okay. So basically, I'm going to have 1 minus 1, 2 times this. And I'm going to change the color here into this and that. Okay. So I'm going to have 1 times 1 minus 2 times minus 1 is plus 2. So that's 3. Minus 6 is minus 3. And then I'm going to have final, this color maybe? It's barely visible. But I'm going to do second row with the second column. So it's 3 times 1 minus 1 is 2. Minus 21 is minus 19. I was trying to go for another color, but this is poor choice. This is a little better. Okay. So this is why I have to have number of elements in this row. It has to match the number of elements in this column in order for this to work. So my dimensions were, this was a 2 by 3 and this was a 3 by 2. These inner dimensions match, and then my result is a 2 by 2 matrix. Questions? So if I formalize this, I will get this element. So let me now learn how to refer to the elements of a matrix. So I'm going to refer to the elements of matrix A by row and column. So I'm going to call A12, or sometimes A12 is going to be element in row 1 and column 2. So basically this matrix here would be A11, A12, A21, A22. Or that's a new, sorry, that's a new matrix C. So I'm going to call them C's in order not to confuse this with the original matrix A. So in general, I'm going to call that Cij, meaning row I, column J. Okay? So I'm going to call these C's as well. So how do I actually get this C11 here? It's actually a scalar product of row 1 in A and column 1 in B. Okay. Ci12 is the dot product or scalar product of row 1 in A and column 2 in B. C21 is the dot product of row 2 in A and column 1 in B. And finally, C22 is the second row dot second column. Okay. So I could have now much larger matrix. Okay. Could be a matrix of 20 by 31. Okay. And my element in 19th row and 21st column, which is C1921, okay, is the dot product of row 19 in A and column 21 in B. Doesn't matter. So my general rule for this multiplication, and the reason why I want to formalize it that way and state it in general terms, is that I need to later on know how to program it. Okay. So basically, in general, Cij is dot product or scalar product of ith row of A and jth column of B. And if it's a dot product, I'm going to introduce immediately a formal way to write it down. So we went first element of that vector, row vector in A, with first element in B, plus second times second, plus third times third, right? And I write that as a sum. So it was actually, for instance, in this particular case, I had 3 elements. So it was AI1 times B1J plus AI2 times B1J plus AI3 times B3J. Okay? Does everybody agree with me? Because my ith row has elements AI1, AI2, AI3. Thinking about that example where we actually had 2 by 3 matrix and a 3 by 2 matrix. And my jth column has B1J. Oh, there's a 2 here. So this 1, 1, 2, 2, 3, 3 are matching, right? So A12 times B2J and plus A13 times B3J. And we are going to write that down using a summation term. Sum for some k from 1 to 3, AI, K, B, K, J. So this is just a way to formally write down those sums. So this sigma is Greek letter, Greek uppercase letter sigma. And it's denotes a sum. A-I-K, B-K-J. A-I-1, B-1-J, A-1-2, B-2-J, A-1-3, B-3-J.
A1 or AI?
I1, I2, I3. That's my ith row. Now, if I had more than one, even more general, okay, I could have M by N matrix A and N by L matrix B. Okay, so my A is M by N, so it means I have M rows and N columns. B is N by L matrix. So if I have C is equal to AB, what is going to be its dimension? First thing that I check is, yes, these inner dimensions are matching. They're both N. So then my result is M by L matrix. And each element of that matrix I can get like this. So every element Cij is sum for k over 1 through what? A, I, K, B, K, J. How many?
That starts with L, or is that one?
I, K, K, J. So how many of these in the sum? N. That's this matrix, this dimension that has to match. So I have matching pairs, right? Okay. So this is this dimension that had to match. All right. So is AB equal to BA? I'm used to that 2 times 3 is the same as 3 times 2 for numbers. How about matrices? Why not?
I don't think we're- 2 times 3 times 3 by 2 would be 2 by 2, but it's 3.
Can I do in this previous case of 2 by 3 and 3 by 2, if I flip them over, I'm gonna have 3 by 2 times 2 by 3. What's the result? So for one, dimensions don't match. But even when dimensions do match, so let's say that all of your matrices are 2 by 2, you can multiply them all day long. A times B will not necessarily be equal to B times A. So that's the fun thing about matrices. Yes?
So if I take like A and B and transpose both of them and multiply them, do I get what the result would have been also transposed?
Yes. So AB transpose is B transpose times A transpose. Okay? Alright. So basically, this is, the answer is no. In this particular case, if I had 2 by 3 and 3 by 2, this would be 3 times 2 times 2 times 3. So the result is 3 by 3. Okay? And that's definitely different from the 2 by 2. This is called, it's not commutative. Not commutative. the way scalars are. Multiplication. Yes. All right, so this is the fun part with the matrices. The easy one that I kind of didn't even mention, but I'm gonna mention it now. 6 is if I had a matrix, and let's go to any matrix, 1, 2, 0, minus 3. How would I multiply this matrix with a number? Let's say 2. Just with one number. Everybody, right? So this would be 2 times 1 is 2, 4, 0, and minus 6. So this is multiplication by scalar is easy. So there's one thing I'm kind of comparing how things work with matrices versus how they work with a number. So if I multiply it with number 1, of course, nothing changes. Is there a matrix? So if I multiply a matrix with that matrix, that nothing changes, that it remains the same? Identity matrix. So if I actually had a matrix, this identity matrix 1, 0, 0, 1, let's multiply that with A. Okay. First, I'm going to have this row with this column. And my result will be 1 times 1 plus 0 times 0. That's 1. Then I'm actually going to do this row and this column, just for kicks. So it's going to be 1 times 2 plus 0 times minus 3. That's a 2. Okay. Then I'm going to do this row and this column. 0 times 1 plus 1 times 0, it's a 0. And I'm going to do this row and this column. 0 times 2 plus 1 times minus 3 is minus 3. So that's, again, A.
How will you know where to put the elements in a corner?
This?
Yeah, how will you know where to
So C11 is first row by first column. C21 or C12 is first row by second column. Okay? So Cij is ith row by jth column. Okay? So basically this is identity matrix that doesn't change anything. And I'm going to call it I. All right, that is it. Homework has been posted, right? You're working on it? Huh? Yeah, it's due on Wednesday.